Alice and Bob are playing a stone game where the stones are laid out in a row and each stone is worth some number of points. Taking turns, with Alice going first, each player blabs either 1, 2 or 3 stones from whatever's left at the front of the row, adding up the values of the stones they take as their score. Intermediate level. Picture 4 piles. 1, 2, 3, 7. Grab the 3 biggest piles first and you bank 6 points, but that leaves the 7 for Bob and he wins. In short, more stones taken does not mean more points won. Here's the setup. A row of stone values, sometimes negative. Each turn, whoever's playing grabs 1, 2 or 3 stones from the front and the value gets added to that player's score. Alice moves first. Both play perfectly. Rows can run up to 50,000 stones, so anything exponential is off the table. Picture 2 kids taking turns grabbing coins from one end of a jar, each playing as smart as possible. That's the entire shape of this problem, and it's the same shape behind a whole family of interview questions. Nail the trick coming up next and you'll recognize it instantly next time. Try a smaller row, 1, 2, 3, 6. Play it out by hand if you want. Alice cannot force a win here, no matter which stone she opens with. The best she can manage is a tie. Hang on to that result, we'll come back to why. 4 tools, and you already know all of them from everyday life. A list is just a shelf with 1 slot per stone. Range counting backward is reading instructions from the last step to the first. Negative infinity is starting so low that literally anything beats it. And max is just picking the tallest of a few options. That's it, that's the whole toolbox. The obvious move is to simulate the game. Try taking 1 stone and recurse for both players. Then try 2, then 3. I wrote this exact recursion my first time through this problem, tracking 2 separate score variables. Total mess. It works on tiny rows, but 3 branches per stone explode fast. We need to shrink this down to 1 number. Which number? Hold that thought. Here's the trick. Instead of tracking Alice's score and Bob's score separately, track 1 number, the score gap. Define DP at index I as the best lead the player whose turn it is can build over the other player, playing perfectly from there on. That's the 1 number from the earlier cliffhanger. Every turn, whoever moves becomes the current player. So the same formula works for both sides without ever naming them. I call this the score gap trick, and it's what turns a 2-player game into ordinary single player. Dynamic score gap trick, and it's what turns a 2-player game into ordinary single-player dynamic programming. So here's the recurrence. DP at index I is the best you can do, choosing to take 1, 2 or 3 stones. Whatever you take gets added to your score, then you subtract the opponent's best gap starting right after your choice. Notice DP at I needs values further along the row, so we can't fill this left to right. We fill it from the back, last stone to first. In short, future decisions get computed first. Say the mover takes 2 stones from the front. Both values get added straight into the running score for this turn. Whatever is left of the row becomes the opponent's row, and they get to play it perfectly too, so their best gap gets subtracted, flipping the sign against us. 1 decision and control of the score gap passes to the other side. The DP list gets 1 slot per stone plus 1 extra for index N, the empty row sitting at 0. We loop I backward because DP at I needs values further ahead that must already be filled in. Inside we try taking 1, 2 or 3 stones. The running take just adds 1 more value each pass, and best keeps the highest score gap across those choices. Alice moves first. So DP at index 0 is exactly her best lead over Bob across the whole row. Positive means she wins, negative means Bob does, and 0 means they tie. 1 line with a chained conditional reads that sign straight into the answer. And that's the whole thing. 1 list, 1 backward loop, 1 sign check at the end. Every piece here you've already seen explained. Quick trace with real numbers. Say we're at index 1 in the row 1, 2, 3, 7 and we take 2 stones. Running take starts at 2, then adds 3, landing on 5. That candidate then subtracts DP at index 3, 1 slot past what we grabbed, exactly where the opponent's turn begins. Let's run the real code on the exact row from the opening 1, 2, 3, 7. We fill backward, so DP at index 4 starts at 0, the empty row. Working back, DP at index 0 ends up -1. That means Alice, who moves first, is 1 point behind Bob under perfect play. So the code says, Bob, exactly what we saw at the very start. Here's a new row. 1, 2, 3, -9. Same rules, both play perfectly. Alice moves first. Pause right now and decide, Alice, Bob, or a tie. Alice's best move is grabbing all 3 good piles up front, 1 plus 2 plus 3, 6 points, leaving Bob stuck with -9. Run the DP and index 0, lands on +15. Positive gap, Alice wins. Same score, gap trick, different row, still clean. First mistake. Tracking Alice's and Bob's scores separately. You end up juggling two arrays for a game that only cares about their difference. Second, sizing the DP list to exactly the stone count and forgetting the extra slot for the empty row, which breaks the first backward step. Third, assuming taking more stones is always better, that falls apart the moment a big or negative value shows up, same as our opening example. You could write this top-down instead, recurse from index I, cache the result, and it reads a little closer to the plain rules of the game. But recursion means stack depth, and on 50,000 stones that risks hitting a recursion limit for no real benefit. I'd always shift the bottom-up loop here. Naive recursion without caching branches 3 ways at every stone and grows up exponentially, while our DP does one pass, linear time, linear space, done. A row of 1 stone, Alice just takes it, nothing to compute. All negative values, the code still finds whichever ending loses the least. If both players' best play lands exactly even, DP at 0 comes out at 0 and we correctly return a tie. And since this is one backward loop with no recursion, 50,000 stones runs just as safely as 4. Remember the greedy trap from the start, grab 3 piles, 6 points, and Bob still wins with 7. That's exactly why we stopped counting stones and started counting the score gap. DP fills backward, 1 number per index, best lead from taking 1, 2 or 3 stones. Check the sign at index 0 and you already know the winner. Score gap DP. Want to take this further? Stone Game 2 swaps the fixed 1 to 3 limit for one that grows as you play. Same gap trick, harder recurrence. Some code is unreadable. This button is unread X. This button is not subscribe. If something feels off or missing or you want to see something new, tell me in the comments.